can proceed. So one of the systems of interest is the so-called quark-gluon plasma, which I think is not a very fortunate name, but people call it like this. So what is this? So this is a state of nuclear matter which can be achieved, for example, in heavy ion collisions. So, for example, achieved by colliding heavy ions in accelerators. And heavy ions, for example, gold or lead, stripped out of electrons in accelerators. And the accelerators doing this are, so there is a purpose-built accelerator which is called RIC in the United States, in Brookhaven. This is relativistic heavy ion collider. It is in operation since the year around 2000 and is working now. Then there is a heavy ion collision program at LHC. So LHC, of course, is mostly known for proton-proton collisions, but they do have, in this typical run of LHC, they have at least 1 month. Then they collide ions of lead with each other. And this will continue for quite some time. And then there are other accelerators, including the ones which are under construction at the moment. And the ones of interest to us will be accelerators which are looking for, supposed to look in particular for the critical point of QCD. And these are accelerators NIKA in Dubna in Russia and FAIR in Germany. So what happens is that there is this collision of these ions, and it produces, so suppose this is a beam of collision. Of course, this is extremely schematic, but nonetheless, so these ions are moving with speeds which are close to the speed of light, and therefore they Lorentz contracted. So these are basically pancakes, in fact, often modeled by infinitely thin pancakes. And they collide with some offset, and they produce this state of nuclear matter with a rather extreme characteristics, I would say. So for example, for RIC, so what we have, so the energy of the beam in the center of mass frame, just to give you some numbers, so RIC is about 200 GeV per nucleon. And the number of participants, so number of nucleons, is about 200. So you can estimate, so typical radius, for example, well, again, so this is schematic, of your nucleus will be around 7 Fermi. So you can estimate very crudely the energy density which is achieved in the result, as a result of this collision. And the estimate of this energy density gives you, so very crude one, gives you that the energy density epsilon is something of the order of 5 GeV per Fermi cube.
Andrei, is it 200 GeV per nucleon?
Yeah, it's pretty, yeah. Yeah. So we will see. So is it a large number or a small number, right? So that we need to compare it with something to understand what this actually means. So how can we compare? Yeah. So also the actual collision, So what happens? So they collide. Of course, it's happening during a fraction of a second, which is comparable to the time which is necessary for the photon to transfer to the size of the nucleus, right? So this is unimaginably short time. So they create this blob of nuclear matter, which of course immediately goes in all directions and hadronizes in small hadrons with all these particles, pions and kains and so on, flying out of this center of collision. And it is registered by these enormous detectors, extremely sophisticated detectors. And experimentalists tell us, and I simply cannot imagine how they manage to do it, but they do manage to do it. They actually are capable of measuring all the characteristics of the particles flying out of this collision center, collision by collision. So there are billions of collisions per second, and they manage to collect all the information about each individual particle, pi and so on, which flies out of this region of collision, and measure momentum, measure the angular various characteristics, and so on. So there's a plentiful of experimental data. And what we want to understand is how to this the evolution. So when you create this state of matter and it disintegrates, it doesn't disintegrate instantly into the particles. It first expands and then disintegrates. And this moment of expansion is modeled by phenomenologists by relativistic NavierStokes equations. So they manage, given this data of the final state, they manage to reconstruct of what happens to this nuclear matter. And of course, nuclear matter theoretically described by QCD. So we are talking about QCD at finite temperature and density, right? The number of participants is sufficiently large. And this fluid, this nuclear fluid, explodes. And this moment of expansion and explosion is described by the usual relativistic NavierStokes equations. But in NavierStokes equations, so equations are the same. NavierStokes equations describe any fluid you mentioned, right? Water and some gases and every fluid and quark-gluon plasma. And what's the difference between, for example, when you write down NavierStokes equations for water and for quark-gluon plasma? What's the difference between the two sets of equations? The difference is encoded in transport coefficients, in viscosities, conductivities, diffusion constants, and so on. Each transport coefficient remembers, it carries information about the microscopic theory this transport coefficient was derived in. So, for example, it's viscosity of QCD, and not any other theory, right? So this is a standard philosophy of effective theory, right? So you describe your system by something sufficiently macroscopic, for example, NavierStokes equations, but these equations do remember through transport coefficients about the microscopic theory which underlies this system, right? It's the same as in quantum field theory. So when you talk about massive electron and various parameters of your standard model, they do carry information. They do remember that something was happening in the ultraviolet at very, very short distances where you have, at the moment, you have absolutely no idea what is actually going on. But the information, the memory of this is encoded in these constants, in these parameters, which enter this Lagrangian of the standard model, or NavierStokes equations in the case which we are going to describe. All right? So this is important to understand. So in order to understand, so people can solve NavierStokes equations, but they need, in order to find the solution, they need values of these transport coefficients in particular. And they also need thermodynamics, right? It's always the same. They need Z, or results of this, right? So they need thermodynamics, and they also need linear response, or they need transport coefficients. For QCD, of course. All right? So this is a question. So, okay, so let's do precisely this. Ambitious title is the following: thermodynamics and transport of QCD from first principles. All right, fine. So we start with LQCD. And if we are ambitious enough, right, so, right, fermions. And in principle, if our tools are sufficiently powerful, this is all we need. Because from this, we are supposed to derive everything about nuclear matter in terms of thermodynamic properties, anything. And also all about transport, including viscosity and everything else. We don't need anything else. So all we want to need is to compute Z for thermodynamics. So this is trace e to the minus beta h, derived from this, h plus mu q, for example, baryonic charge. And how can you proceed with this calculation? Well, in quantum mechanics, we did it in a simple example of oscillator, right? We just took a trace, we knew the quantum states, right? We summed over states n of harmonic oscillator and happily derived this expression 1 over sinh, right? Remember. Now, in quantum field theory, it works more or less in the same way, except that it is very convenient. So you have this formula of trace, which means you have these brackets, Brian cat, right? So, of something, of some operator. And you remember very well the functional integral representation of some amplitude, the transition amplitude, e to the I h t minus t prime, right, from state initial to final, right? So Feynman told us how to write this as a functional integral. And this is almost this, right? The only thing is that it's not a transition from initial to final, it's a trace. So the final state and initial state is the same. And you have to sum over all of them. So it kind of smells that you can, in principle, write down this expression as a functional integral. And people did this in the 70s. So this is written. I will not do it in detail as functional integral of certain type, functional integral. And therefore, all the machinery of quantum field theory can be applied, in particular perturbation theory, so you can write down Feynman diagrams and so on and so forth. They will be, this will be a quantum field theory at finite temperature and density, because it's not quite the Feynman setup. It will, you have to take the trace, and therefore your fields become periodic and so on. So I will not go into this detail. So again, this is hyperlink. If you are interested in the subject, please take any book from the list that I provided you on quantum field theory at finite temperature and density, and learn the subject. It's quite interesting and captivating. All I want to say here is that computing perturbatively, so for example, Feynman diagrams at finite temperature and density, so take your favorite model theory, like lambda phi to the fourth, right? And compute free energy of lambda phi to the fourth. Using functional integral representation, you will discover that this computation is much more complicated than computing things at zero temperature. So at finite temperature, there are additional complications in perturbation theory, and people spend years and years and years trying to refine this perturbation theory and do resummations, and this is all very complicated. So in general, it's more complicated than doing the same calculations at zero temperature, although zero temperature calculations, as you well know, are sufficiently hard. Okay, functional integral. So this can be treated perturbatively. If you have small parameter, or it can be treated non-perturbatively. And this usually means on a lattice. Okay. So these are two approaches. So once you know Z, everything follows from free energy. So this is minus T log of Z. And you can compute, for example, pressure. So pressure minus d omega over dV at fixed T and mu. Or you can compute entropy. So these are wonderful objects which you want to know, pressure and entropy. Well, parameters of QCD, right? Of course, QCD gives us very few parameters to deal with. So one of them is number of colors. So you can try the 1 over n expansion. In doing that, there is also a number of fermions. You can try to do something with it. But as we all know, the perturbation theory, which relies on alpha strong being small, will not tell you the truth if alpha strong in the real process happening, for example, in these heavy ion collisions, is of order 1. So you may suspect, you can still try and hope that the truth is not very far from your calculation, and we will see in a second whether this is correct. But in general, you understand that perturbation approach, once your alpha strong is of order 1 or more, is not very reliable, in particular for thermodynamic and transport properties which we are interested in. What about the lattice? You say, well, fine, who cares? I'm in non-perturbative domain, I just put everything in the computer and calculate whatever I want. And to a large degree, this works. For example, if you're interested in thermodynamics, so lattice, it works pretty well. So thermodynamic quantities can be computed, and we will see again in a second the result of this computation. Unfortunately, it doesn't work so well if you are interested in transport properties. So if you want to compute viscosity or thermal conductivity of your quark-gluon plasma, you cannot really put this on a lattice and do the computation. The reason for that is very simple. When you are interested in transport properties, it means that you are interested in real-time processes, right? So you need to create some disbalance of charge, so there will be a flow of charge in time. You will write down diffusion equation. Diffusion equation, remember, d over dt, right? So there will be some real-time processes which will be necessary to deal with when you're describing the system. But on the lattice, you are doing computation in Euclidean time, right? So because you need a well-defined measure, e to the minus s Euclidean, which allows you to actually do something convergent, right? You cannot do these computations with e to the is, right? Because the thing will oscillate. Of course, people still try, so there are various methods. So modulo all these attempts and so on. So strictly speaking, if somebody asks you, okay, compute, give me viscosity of QCD from the latest computation, the answer is there is no reliable way to do it because it's real time, it requires to deal with real-time process. So, so lattice gives you thermodynamics, but not transport. So this is a big problem. Still, so let's see. What you can do in terms of this fundamental computation, right? So let's compute pressure. Let's compute pressure. This is a relatively straightforward calculation. And you don't even need the functional integral in first approximation, right? So what kind of approximation we are going to do, right? So we will pretend, of course, so it will be perturbative calculation, and we pretend that our alpha s is actually a parameter, which is, of course, energy dependent, but let's pretend it's a small parameter. And moreover, we start by just setting alpha s precisely to 0. It can happen, it's asymptotic freedom, right? So what this means? It means that we switch off completely interactions between quarks and gluons. So what do you have as a result? You have an ideal gas of quarks and gluons, right? So you have some bosonic and fermionic degrees of freedom. Yes, relativistic, that's fine. But fundamentally, this is not very different from a gas of photons, from black body radiation, which we all know how to compute in statistical physics, right? So all properties of black body radiation, this is ideal gas of photons. I have ideal gas of gluons and quarks, but fundamentally this is the same type of calculation, which is described in any book on statistical physics, including Landau-Lifshitz, volume 5. So, exercise for you. Show that the pressure in QCD, so this is SB is Stefan Boltzmann, right, so ideal gas, is actually given by the following simple formula. I deliberately put a number of fermions unspecified. T to the fourth plus some corrections which go in powers of m times t, where m is the mass of whatever is massive in your theory, for example, some quark. Okay? Now, this 8 here it knows something about nc being equal to 3, right? N squared minus 1. But anyway, so this is a contribution from the ideal gas of quarks and gluons. And what I want to do is to compute pressure of QCD in perturbation theory, where I have Stefan Boltzmann contribution, which means alpha strong equal to 0, plus corrections. Plus corrections, like this. To do this, I use the functional integral representation of z, and then pressure is this derivative with respect to volume. So in principle, this is known how to, or we know how to do this computation. So what is the? Let me show you the plot. It's a plot of pressure in QCD or our gauge theories, normalized by Stefan Boltzmann. I will divide by Stefan Boltzmann as a function of temperature. Also normalized by some critical temperature. I will explain in a second what it is. And so here we have 1. So what happens? If the temperature is infinitely high, so I have infinitely hot gas, which means infinitely energetic. So my system is at infinite energy, and it is asymptotically free. That means that in the limit of t going to infinity, I will have ideal gas of quarks and gluons. My approximation of ideal gas should be perfect in this limit. So somewhere here, at 1, my perturbative calculation, this one, is valid, except that I normalized by PSB, so therefore I will get 1 here. Somewhere, this is ideal gas.
Sorry, is this P in the denominator corresponds to the experimental result?
No. This is all theoretical, right? So
what is this P then? P over PSB?
So I will tell you in a second, right? So we are trying to. So suppose we have Lagrangian of QCD, right? And I want to extract as much as possible from Lagrangian by various means. For example, by perturbation theory, and also by the lattice. Okay? So all I'm going to show here will be theoretical, extracted from this LQCD by any means I can. All right? So in particular, I know that here the result will be 1. Okay? And I can compute a number of Feynman diagrams. In fact, people can compute 6 loops and so on, right? So it's quite, and continue this line, theoretical line, right? But I also can use lattice. Then alpha is not so strong, right? So I can combine these two things, right? So let me show you this plot. And the plot goes like this. So again, so you may think of this as a lattice result combined with perturbative QCD at finite temperature intensity. Okay? And this is schematic, of course. So what this plot shows is the following. Indeed, if you step away from ideal gas, then this dependence is very small, right? So you almost have ideal gas for a long, long time, plus a little bit of correction. Then you come to some region where what you see is not, strictly speaking, a phase transition, but it's a crossover. But still, it's a qualitative change in behavior of your system. Then the pressure or whatever, you can also compute energy density or whatever quantity you want, drops very strongly. So this is known as a crossover. So this is T over Tc. So this Tc is determined from the lattice, and it's about 170 MeV. And this is known as a crossover from the hadron phase to a quark-gluon plasma phase. Okay? So in some sense, in very crude sense, right, when you have a transition, for example, when you ionize a gas, like for example in these day tubes, right, so by applying some external electromagnetic field, you have a transition from the bound states into the plasma, right? When you have electrons and ions, they are free to roam around the volume. And something similar, philosophically speaking, happens here. So you have, on the left, you have the hadron gas, right? Far to the left, you have the hadrons, which are bound states in some sense of quarks and gluons. And then, if you apply sufficiently high temperature, you melt those hadrons, and then quarks and gluons are free to roam in whatever volume they have. All right. So then you have sudden increase, if you want, in the number of degrees of freedom, because all these quantities, of course, they are proportional to the number of degrees of freedom in your system. And then you have a sudden increase. It means that yes, the system melted. Now the fundamental degrees of freedom are individual quarks and gluons rather than hadrons, bound states. All right. So this is what we see from the lattice, combined with perturbative calculations. But again, so this is what Lagrangian of QCD tells you. And this is what these accelerators actually see. Of course, it's not that you have this little box and you dial some knob and you look at the system and it tells you, no, this point corresponds to it. So it doesn't work like this, but based on some measurement of these hadrons which fly out of the center of collisions, you can say certain things about the phase diagram, and it more or less matches our expectations. So this is fine. Yeah.
Is it related to inflection point or something? Is it just a coincidence?
So this is just a, no, it's a mathematical property. So you can say it's a smooth curve, right? So the crossover, so it's not a situation where you have a finite size system, right? And if you take the infinite size, then you will have a genuine phase transition. No. This is just a sharp rise, which is called crossover, right? So mathematically speaking, this curve doesn't have any singularities. Right? Because in real phase transition, then you take a thermodynamic limit, right? You discover some singularities in your, maybe in some derivatives of your free energy, right? Here, no, it's a smooth curve. But it's a crossover. So you can have you can play with number of bosonic and fermionic degrees of freedom in your Lagrangian. So take something different from QCD. So for example, I don't know, some number of generations, change it, right? And you can get a model in which you have a genuine phase transition here. So this is all sort of model dependent, right? So but in QCD it's a crossover.
If you had a third axis of the chemical potential, how would that surface look?
Yeah, I'm about to say precisely this, because remember I had a drawing of a phase diagram of some a liquid or methane or some other substance. So using tools of this type, let's try to draw the phase diagram of QCD, right, of nuclear matter. So what is known about this? And this is related, of course, to Subir's question, because in addition to temperature, we also have chemical potential in the game, the baryonic chemical potential. So, okay, so let's.
So, excuse me.
Yeah.
This is for real QCD.
Yes.
But there's an idealized limit of QCD where the up and down part masses are zero.
Yes.
In that case, there actually is a real phase transition.
Yeah,
So,
exactly.
So it's not so far away from real QCD, which is why this curve is so sharp.
I agree. Yes. Yeah, that's right. Yeah. There is a list of various cases like the one you mentioned, where people sort of played with what kind of transition you get depending on what degrees of freedom you have. Yeah. So I think this is all pretty well studied and mostly in the lattice.
It's known to us. It's not known to these people.
Yeah, that's right. Yeah.
It's mainly the massive strange quark that converted it from
to a crossover. Yeah, possibly so. Yes, I think that's yeah. Right. So again, schematically, what can we say about the full phase diagram, where now we have a baryonic chemical potential, say QCD phase diagram. And so you have one axis where you have now temperature, and another axis where you have a baryonic chemical potential, mu baryonic. And again, schematically, the diagram looks like this. So I will say a few words in a second. I mean, of course, you can find pictures where this is done more precisely, but let me be schematic. There is something which is called CFL. I will explain in a second. Right, so then there is this transition. You have nuclei, you have vacuum, here you have hadrons, and here you have QGP. And this is this crossover that is shown here, and neutron stars live somewhere here. So the commentary is the following. this diagram is not very well known, right? It's very difficult to access experimentally. So for example, if you have very, very high density, so this axis tells you that things are extremely dense. So for example, you can look at cores of neutron stars and all these objects. And of course, it's extremely difficult to learn what is inside there. And this is an ongoing, sort of, you try to kind of interpret various signals from astrophysics in order to say something about the equation of state of this matter inside the stars and so on. But schematically, the situation is the following, that we have a transition between the state of matter, which is known as quark-gluon plasma, and hadrons, and this is the line of this transition, and the line of this transition is supposed to end, or at least conjecture to end, in a critical point, pretty much like the line of phase transition in water. So this is critical point, possibly, right, because this is not known, let's say, experimentally, and one of the purposes of these new accelerators, such as NICA and FAIR, would be to explore the phase diagram in the vicinity of this critical point and see perhaps maybe there is some signature of the presence of this phase transition, right? So I remind you that critical point is a very special point in the state of matter, right? So there is this wonderful phenomenon of critical opalescence, right, which you probably had seen in experiments, right? When you reach a critical point for water, for example, or basically for, well, actually for some other substances with lower critical temperature, but nonetheless, when the transition, the sharp transition between liquid and gas disappears, and you have this suspension which is kind of neither, right, liquid or gas, and the scattering of light or scattering of our particles, for example, neutrons, show that all the characteristics of this phase transition. This is a wonderful stuff. But so QCD in principle is conjectured to have this critical point, and these accelerators will try to get a signature of it. But RIC and LHC, so this plot here is describing the transition or crossover somewhere in this area. Crossover transition. So this is very small or zero chemical potential and temperature of this type of 170 MeV. So we are sitting somewhere here. Now, the right-hand side of this diagram, it's all conjecture. So this is all, it's extremely interesting work on, so this is a color, flavor, log, phase, and so on. So, but again, so there is no experimental access to this area, and also it's very difficult to compute things from first principles when you have region at a temperature which is not very small and chemical potential which is large. So this is where the heavy ion collisions are happening and described. But I remind you that the phase diagram, when you say words phase diagram, it describes you equilibrium properties of matter, right? And of course, when you smash ions, it's nothing but, you know, it's not an equilibrium situation, right? So you don't wait there until your soup boils and so on. So it's a highly non-equilibrium process. Therefore, you have to describe it by using NavierStokes equations and transport properties and so on. So fine. So we have some control over thermodynamics, not great control, but some control. Let's see what we can say about transport properties, and in particular viscosity, QCD. So, so let me see. Yeah, in order to do this, so my goal actually to write down the Kubo formula for viscosity. Let's see if we manage to do it today. And for that, we'll need, again, some standard tools. So we will use the expectation value of the stress energy tensor operator. And in any quantum state, so this may be equilibrium or non-equilibrium, doesn't matter, so you can, we will specify which quantum state we are talking about, and we'll denote this by simply T mu nu without any brackets. This is not an operator, this is the expectation value. It's a function of x. And then, in equilibrium, you can compute T mu nu, for example, at finite temperature, and you know how to do this computation. In principle, you have trace rho t mu nu, and this can be converted into Feynman integral, and you can do these computations. But you know that if you're talking about the sufficiently macroscopic system, so the system on large scales at large times, then in equilibrium, the expectation value of t mu nu for isotropic system will have this form. All right. So for people who are puzzled why this is so, it's a hyperlink, Landau-Lifshitz volume 2, right? So this is Pascal's law. This is energy density, pressure, pressure, pressure in all directions. I won't spend any time describing it. Ask me or read the appropriate book. So why this is so in equilibrium? It must be so. Of diagonal terms is 0. So this is isotropic homogeneous system in the reference frame of the fluid. So the fluid, relativistic fluid, is in front of you. It's not moving anywhere. Now suppose, so this is in reference frame of the fluid. Now, if the system moves, so if system moves with for velocity u mu, so gamma is 1 over square root, right? So then the same equilibrium expression can be written in the following way. So let me write down and explain. So this delta mu nu is a curious object built out of for velocity. So u mu is the for velocity of the system, right? So what is written here is the same as this, but now your fluid is moving somewhere with constant velocity u mu. So all patches of fluid are moving with the same velocity u mu relative to u. So then you can derive this by 2 ways. I mean, one of them is sort of the honest way you do the Lorentz transformation, right? So this is a tensor, right? So you switch to the reference frame, which is moving with constant velocity u mu, given explicitly by this, and then after some struggle with form, okay. After some time, you arrive to this expression. So eta mu nu is the Minkowski minus 1 plus 1 plus 1 plus 1. A better way, a simpler way to do it is just to ask yourself the question, what kind of relativistic object with 2 indices, which is symmetric, you can build out of ingredients available to you. And ingredients available to you are for velocity and eta mu nu. So there is a standard way of doing this. So you write down this expression with unknown coefficients here and unknown coefficient in front of this delta, and then ask that in the reference frame of the then the fluid is not moving. It means that you only have C and 0. So this is rest frame. It reduces to this expression reduces to this t mu nu, and then it fixes your coefficients epsilon and p. Okay, so again, this is an exercise, or if you want a hyperlink, if you haven't derived this ever in your life, please, now is the moment. So please do it. We are interested in a more complicated situation. Namely, now we want, so all of this is in equilibrium, and the thing is moving relative to u. That's the worst thing that can happen. Now, I want to consider the situation in which our velocity for velocity u mu is not constant. So each region of liquid can have dependence on time and space. So I want to see what happens then u mu depends on t and x, right? Then in principle, there could be complicated motion, turbulence, and everything else, okay? Well, here we built an expression for t mu nu in equilibrium by saying that we only have 2 ingredients, u mu itself, which was constant, and eta mu nu, Minkowski tensor. Now, when you have dependence on for velocity, or for coordinate x, you can also have other ingredients which have the right number of indices. Namely, you can have derivatives, for example, d mu u nu, right? And if you want symmetric, you can symmetrize it, right? You can write down d nu u mu divided by 2 and so on, right? And in fact, you can have infinite number of these objects, because now you can take as many derivatives of u mu. U mu is now a function of x. You can take as many derivatives of u mu as you want and combine some of them, right? So that only 2 indices are remaining, 3 indices are remaining. So you can have the whole tail of these derivatives in addition to what is written here in equilibrium. So once you relax this condition of equilibrium, you can write down the infinite tail. And this infinite tail is very suggestive. So let me write it down as an addition to this. And let me write it down in the following form. So our T mu nu will be T mu nu 0, which is present here, plus T mu nu 1, plus T mu nu 2, plus so on. And this 0, 1, and 2 will be number of derivatives of u mu. All right? So, so here in T naught, T0, we have no derivatives of velocity. In T1, so let me just write T1. This expression looks a little bit involved, but only before you start dissecting it. And I will write this in d dimensions. All right, so this is T1. So what happened with T1? So T1, by construction, so this is known as a derivative expansion, by the way. So in T1, I have terms which involve first derivative, one derivative of u mu. Only one derivative of u mu, no two derivatives, okay? And I wrote it in a certain way which is useful. There is a decomposition, so we have a tensor with two indices, and I can decompose it in a certain useful way. So for example, if I have a vector, so suppose I have a vector a mu, and I have another vector here, which is a special vector of my 4 velocity. So I can always decompose u mu in the part which is parallel, so to speak, to velocity and perpendicular to it. So in the longitudinal and transverse part, right? So I can do this decomposition. I have a mu which is parallel and a mu which is transverse, right? I won't do it, but I'm sure you all can do this decomposition, right? And I can do the same thing with tensors. I can take my tensor of second rank and decompose it in a transverse and longitudinal part. All right? And this is what is done here. And again, I won't, due to lack of time, I won't go into detail how precisely this is done, but you can guess that this is done with the help of this wonderful projector, delta u mu, because it has this interesting property. And it's not an accident that these projectors appeared in this decomposition. And the idea is very simple. You want to extract independent pieces of your tensor, right? Because whatever multiplies the independent pieces is the information which you want to extract from your theory. The rest is just indices, right? So the rest is known. So please read Kovtun's lecture notes in order to understand deeper how this decomposition happens. But I hope, at least philosophically, this should be clear. The coefficients which multiply these two independent pieces are known as the shear and bulk viscosities. So this is shear viscosity, this is bulk viscosity. And these are two transport coefficients which characterize homogeneous and isotropic relativistic system of any kind, not only QCD, any kind. All right? Fine. What happens next? Our energy momentum tensor is a conserved quantity. It obeys an equation d mu T mu nu equal to 0. And by the way, for future reference, let me just mention that if I wanted to write down, so I wrote everything in Minkowski space-time, but nothing prevents me in principle to write this down in curved space-time. And we know how this happens, right? I have to replace, so here I have to replace my eta mu nu with generic g mu nu. And whenever I have the derivatives here, for example, d alpha, d beta, I replace them with covariant derivatives. And here it is in the curved space-time. So in principle, you can write down this expression in the curved space-time very easily. Now, what happens? So this is an infinite expansion. Each term has its own number of derivatives. 0 derivatives, 1 derivative, 2 derivative, 3 derivative, and so on. So derivative expansion of T mu nu. And I have a conservation law. What happens if I combine conservation law with the explicit form for T mu nu, like this? This is an exercise for you. Do it at least once in your life. This is very important. If you only limit yourself with T mu nu node, and you combine conservation plus this, you will get Euler equation for liquid. Relativistic. If you combine conservation law with with zeroth order and the first order in this expansion, you will get NavierStokes. Then you continue, and you can get an infinite number of these equations. So for example, you can write down a similar expression for T mu nu 2. It's far more complicated than here, but you can do it. And then you combine conservation law with all three pieces, and then you get something which is known as Barnett equation. Yep.
All these equations independent because they are counted like Bogoliubov chain.
No, they will be independent because you may ask, well, I mean all the, so when you, so suppose you limit yourself only with T node and T1, what you get is NavierStokes equations which are completely fixed. I mean, it's a system of coupled, of course, but it's a system which is not coupled to any other degrees of freedom within the limits of your approximation. So approximation that you are doing, similar to Bogoliubov chain, right, is this. You chop off the whole infinite tail. So if you didn't do this, right, so suppose there is this infinite tail here, and if you combined this conservation law with a full infinite tail, you would get the full equations, including all microscopics that theory knows about. But when you chop, you take away all the ultraviolet effects in the theory, and you are left with more and more softer and softer sort of infrared description. And so this approximation, similar to Bogoliubov chain approximation, is chopping these pieces. Okay? So NavierStokes, well, Barnett equation, well, I can tell you, NavierStokes equations are complicated enough, right? So dealing with Barnett is much more worse. In practice, nobody does this, but in principle, this is how hydrodynamics is built. This is the fundamental approach to hydrodynamic approximation. All right? So this is essentially the end of today's second lecture. But let me mention two things before I stop. One thing is the following. So first of all, here we took an example where I only talked about the conservation quantity, which is T mu nu. We can build the same story, right? We built the same type of machinery for something simpler, which is, for example, conserved current. So suppose you have a current which is conserved in your theory, relativistic theory, and an exercise for you, build a similar scheme. So write down how J mu can be effectively written as a perturbative expansion, as an expansion of this type, J mu naught, J mu 1, and so on, combined with conservation law, This is actually technically easier than deriving NavierStokes from this scheme. But do both. I mean, do this exercise first, combine this, and derive relativistic analog of a diffusion equation in this scheme. Okay? And again, if you are stuck, please consult Pavel's lectures. This is a wonderful source of this of this stuff. Now, the last remark for today is the following. So you may say, great. So you showed us how to build relativistic hydrodynamics from scratch, more or less. But this is all well known. I mean, it's not really something fundamentally new. Why are we so concerned about these matters? Why do we want to analyze in detail what happens in this expansion and so on? So there are several obvious questions which I haven't mentioned. One of them is the following. How many independent ingredients do you have in this expansion, right? So we started with writing T1, and I said that for T1, there are two independent quantities which carry out all microscopic information about the underlying theory, for example, QCD. There are two of them, shear and bulk viscosity. You go to next order, to order T2, and you discover that there are 15 of them. Then you go to order 3, and you discover that there are 64. And the simple question is the following. If you go to order n in this expansion, how many transport coefficients independent? How many new transport coefficient you will find? The answer to the question is unknown. Nobody knows, but it's not a very difficult exercise to do, actually, so maybe one of you wants to do it. Because you may ask also the following question, how this number grows with n? Is it a factorial growth? Is it exponential? I mean, how precisely this scales with n? And this is related to the fact that when you deal with hydrodynamics, at some point you want to know where your hydrodynamics breaks. This description actually breaks down. And this depends on when your series, the appropriate series, such as this one, start to diverge. Right? I wrote a formal series. This is a formal series. I didn't tell you what the small parameter was in the series, so that you could say, oh, this is my small parameter epsilon, and epsilon is less than 1.7. The thing is convergent, and then it diverges, right? So these are open questions, which nobody actually knows how, well, we know how to address them, but it's rather difficult to do. In particular, just to count the number and the scaling of the number of transport coefficients is a rather complicated task. And all of this is related to the experiments which are done not only at RIC, but also done with hydrodynamic systems in a desktop experiments, because you can have various systems which involve, for example, cold atoms. The number of participants is about 10,000 as well, and they are strong coupling, and you can do whatever you want with them. You can fine-tune parameters, magnetic field, and so on, and you can study the hydrodynamic regime of this system in a desktop experiment. And you can ask, in particular, when the hydrodynamic description of your system breaks down. So we will try to approach this from a theoretical point of view. Now, to finish, so these two lectures were about, so this was motivation to actually explore a different tool to compute this object Z and to compute linear response in the regime where you don't have perturbative access. And this tool is holography or gauge string duality, and this is what we'll explore on Thursday. Right, so we'll stop now and see. So if you have questions, please just